Okay, in this video, I wanted to walk you through a mental shortcut that I use when I visualize a second order Laplace transform term. All right, so a second order term would look something like this. All right, so I wrote one down with specific numbers in it just so it'd be easy to go ahead and take the inverse Laplace transform. So this is second order because if you look at the roots, I have this written in the completing of the square form, and so I actually have done this enough where I can look at, by inspection, the root for this is -2 plus and minus j6. All right, so you take this part, that's the alpha. All right, here's alpha, negative alpha. All right, and then this is plus or minus square root of 6 squared, so that'd be 6. All right, so that's to complete the square form. I use that a lot for the way I think about complex poles. All right, but you don't need to know that. You have this expression, and if you were going to do the inverse Laplace transform, probably like you did in your DiffyQ class, you would consider the sinusoidal component because that has an inverse Laplace transform that looks like beta over s plus alpha squared plus beta squared. Okay, this first term. And then you'd look at also the cosine, e to the minus alpha cosine beta t component, because that transform has this form where it's s plus alpha over s plus alpha squared plus beta squared. All right, so hopefully you've seen these things before in a differential equations class. So effectively, these things that I'm highlighting in pink, all right, these are the Laplace transform pairs. And your task in DiffyQ was to come up with the final expression for the time domain inverse of g of s. Okay, so we've identified alpha to be 2, beta to be 6, and the denominator looks like this, complete the square form. All right, so from there, I can look at my original transform. I have a 3s plus 4, but I see that what I needed, let me use the eraser here, but what I needed was an s plus alpha. All right, so that's what I need. So I put down what I need. All right, s plus alpha goes here. There's a 3 out front, and so I go ahead and put that 3 there. All right, so now this term that I'm highlighting in blue, that's a perfect match with the Laplace transform table. It looks like the Laplace transform scaled by the number 3. All right. But that's not what we have. If you distribute this 3 across, this would be 3s plus 6. And what we have up here is a plus 4. So we have to subtract 2 to make that work out. Okay. Next, we say, all right, well, this term that I'm highlighting in gold, this term matches the Laplace transform table. It's just got a scale factor of 3 out front. But this term, what you need is the factor of 6 because the Laplace transform has a beta on the top. So I get this 6 on the top, and I want it to end up still being 2. All right, so I have to divide by 3. 6 divided by 3 is equal to 2. Okay? And so from there, I can now take the inverse Laplace transform. Hopefully you've seen this kind of thing before, and I get these terms. Okay? All right, so that's a lot of grungy detail, and the good news for you is I'm not expecting you to have to go through that on exams, okay? If I wanted to do it on an exam, I would let you use MATLAB to go through all the grungy details. All right, so let's now pick this up and say, all right, we know g of s has this inverse transform. I'm going to highlight that in green. Here's the inverse transform. It's got 2 components, a sine component and a cosine component. All right, so any second order system can be broken up into a sine component and a cosine component with a real exponential multiplying the whole expression. All right, so often you'll hear me talk about, well, let's make this alpha e to the minus 2t cosine 6t minus phi. All right, so I have two parameters, alpha and phi, that actually depended on how you do the inverse Laplace transform. Okay, so I'm not too worried about that. What I'm wanting to concentrate on is these two factors, e to the minus 2t, and the fact that this is a sinusoid with some kind of phase shift. All right, and so what that lets me do is take a mental shortcut, and I would think, okay, if I had this, I know this is a exponential that's decaying. Okay, and so if I wanted to plot this term, I know that it oscillates in and out of this decay because it's got this cosine component to it. All right, so the point is that the two terms can combine together using a trig identity to a single component, single sinusoid component with a phase shift. All right, so that's the mental shortcut that I'm going to let you use for this class, is that a second order Laplace transform term will turn into some kind of scale constant alpha and a phase shift phi. All right, now the way this would work out is you use a trig identity, so you take the magnitude of the cosine part, you'd square it, the magnitude of the sine part, including the minus sign, you square that, and then you take the arc tangent and plug into this expression, and it turns out that's exactly the same. All right, so I'm going to show you that real quick in MATLAB, but that's the mental shortcut that we're going to use from now on. All right, here's some MATLAB code that reinforces the inverse second order Laplace transform material that we've been discussing. Okay, so we start with our example G. All right, so it's defined just as we did before, where G is equal to 3s plus 4 divided by quantity s plus 2 squared plus 36. Okay, so I wanted to break this up into two different components, all right? So I think it's fairly obvious that from the root locations, you have a root at s equal minus 2, and then you have imaginary roots at plus or minus j6, that the form of the solution is going to be an exponential e to the minus 2t times both a sine component here that we have for S1 and a cosine component that we have for S2. All right, so the weighting on those two components will change depending on how the coefficients work out. All right, so what I wanted to show you first was you can take the Laplace transform of both S1, and here you get the constant term. The constant term is associated with e to the minus alpha t sine omega naught t. All right, and then you also get the cosine term. All right, so here you have s plus 2. All right, so you have that real root showing up as a 0 in this particular case, and that's associated with the cosine term. All right, but if you go back to our original Laplace transform, when you do the inverse Laplace transform, you get g of t. All right, so g of t turns out to be 3e to the minus 2t, and then you have coefficients in front of the individual cosine term and sine term. Notice the frequency is always the same for these. All right, now here's a tip that I have for you that I want you to be able to know about. If you use this VPA command, VPA stands for variable precision arithmetic, and that's the way to force the symbolic part of MATLAB to actually give you some numbers. All right, so in some sense, I think that G is, when it's cast into 4 decimal point numbers, is a little bit easier to look at. All right, and it's certainly easier to use for Canvas quizzes. All right, so the next thing I wanted to talk about was that whenever we do the inverse Laplace transform, you can put this in the form of alpha e to the minus 2t plus cosine omega naught t minus phi. So the key here is I want you to look at alpha and phi. All right, so in the video last time we said alpha, let me get the marker here. Okay, alpha can be found by using a trig identity where you take the cosine part, square it, the sine coefficient, square it, and take the square root. That gives you the magnitude of this decaying exponential term. Okay, and then you can get the phase component. I use the arctan2 function here, where you take the sine component, minus 1/3, and you divide by the cosine component, which was the 3. All right. All right, so if you do the arctan2, that takes care of quadrants, and you don't have to worry about quadrant conversion. And then finally, f turns out to be alpha e to the minus 2t times cosine 6t minus the phase shift phi. All right, so symbolically, this is what that would look like. If you convert that to numbers, you see it's the alpha, just a number, and then a phase shift, okay? And so the next part is simply to convince you, let's see if I can get that to scroll down. The next part is to convince you that f and g are in fact equal. And so I plotted both these on the same scale, and you can rerun this. If I comment this out and rerun it, okay, you only get a single plot. And then if I plot both and hold the axis, so I'll rerun this now, you see the two plots line up right over the top of one another. So f and g are in fact equivalent. All right, so hopefully this helps you with a mental model on the inverse Laplace transform for complex exponentials. And we can use that as a mental shortcut where we just think of this as a single term rather than a sine and a cosine. Think of it as a single sinusoid with a phase shift and a decaying exponential.